This is part 1 of Module 12, Steady-State AC Circuit Analysis using the Phasor method. Let's begin by describing what a phasor is. A phasor is a rotating vector in the complex plane. This is to help you visualize what a phasor is. This is our complex plane, and you see the rotating line segment within that plane. It's rotating at an angular frequency of omega radians per second in the counterclockwise direction. Omega is equal to 2 pi times f, where f is our frequency in cycles per second. Because it is in the complex plane, a phasor will have a real component and an imaginary component. And because the phasor is rotating, both of these components will be time varying. The top of the figure shows how the real component of the phasor varies with time. Note that it is sinusoidal in nature. Let's say that A is a phasor whose angle with respect to the real axis is alpha at t equal to 0. The real component of the phasor is given by this expression. Let me further illustrate that. Let's say this is my complex plane. I have my imaginary axis and my real axis. And let's say that at time t equal to 0, this is the position of A. So this is in a magnitude of A, and this is at an angle of alpha. After some time t, because this is rotating in the counterclockwise direction at an angular frequency of omega, the position of the phasor is going to change. So let's show that. Let's say originally it was in this position. Now, after some time t, it will be in this position. So originally it was at an angle alpha. Now it will be at an angle omega t plus alpha. What is the real component of A? Well, the real component of A is this. And if you take a look at the figure, the real component of A is simply the magnitude of A multiplied by the cosine of omega t plus alpha. So take note that this is exactly identical to this. Let's talk about notation. A phasor is specified by a magnitude and a phase angle. The phase angle is the angle the phasor makes with the real axis at t equal to 0. So if we take a look at this previous slide, this alpha here is actually our phase angle. A phasor actually has a third parameter, omega, because a phasor rotates in the counterclockwise direction with frequency omega. However, omega is an implied parameter. In other words, to specify a phasor, it is sufficient to specify just the magnitude and the phase angle. Now, if you will recall, a complex number in polar form is specified in exactly the same way. You specify its magnitude and its angle. How then do we differentiate between a phasor and a complex number? If you see a number written in this manner, this is a complex number. If we wanted f to represent a phasor, how should we write it down? Well, we should add the argument j omega. That is to differentiate f from being simply a complex number. So the j omega will indicate the phasor nature of f. What is the difference between the two? Remember that a phasor is rotating in the complex plane, whereas a complex number is just a point, a stationary point in the complex plane. The two are very different, and therefore you have to distinguish the two when you write down quantities that are phasors as opposed to complex numbers. Now sometimes it's quite cumbersome to have to write j omega, so there is an alternative notation, and that is by putting a vector arrow on top of the variable. So for example here, because there is an arrow on top of f, we know that f is a phasor. A phasor diagram is a snapshot of the phasor in the complex plane at time t equal to 0. So this is an example of a phasor diagram. It shows two phasors, A and B. What is the use of a phasor diagram? Well, a phasor diagram is used to show the relative position of phasors with respect to each other. For example, in this particular phasor diagram, I know that A leads B by an angle thetas of A minus thetas of B. This angle is thetas of A minus thetas of B. How do we know that A leads B? Remember that these are both rotating in the counterclockwise direction at an angular frequency of omega. The phasor that passes the real axis first is the leading phasor. So in this case, A will pass the real axis before B passes the real axis. So we say that A leads B or B lags A. In the Phasor method of AC circuit analysis, we are going to transform our AC sources into phasors. And this is the rule for the transformation. If we have a sinusoidal quantity of this form, we transform it into a phasor whose magnitude is the amplitude of the sinusoidal quantity divided by the square root of 2. And the angle of the phasor is just the phase angle of your sinusoidal quantity. Observe that if we remove the square root of 2 in the above rule, f of t would be the real component of the phasor f of j omega. Recall from the previous slide that the real component of f of j omega would be f of m over the square root of 2 cosine of omega t plus alpha. So if I take a look at this and compare it to this, they would have been exactly the same if I had removed the square root of 2. The transformation adds an imaginary component to transformed AC sources in a circuit. So originally, our quantity is purely real. When we transform it into a phasor, we are adding an imaginary component. Now, due to superposition, whatever resulting voltages and currents in the circuit will also have imaginary components. That is, the resulting voltages and currents will also be phasors. If we want to get the time domain response from the phasor response, we perform the reverse transformation according to this rule. So this is the reverse transformation. What are we doing here? We are effectively ignoring the imaginary component of the phasor and retaining only its real component. Are we justified in doing that? Yes, because when we did the phasor transformation, we added imaginary components to our sources. Thus, when we do the reverse transformation, we are justified in removing the imaginary components from our resultant phasors. The square root of 2 was introduced in the transformation so that the magnitude of the phasor is the RMS value of the time domain function. That's more apparent from here. If we take a look at the magnitude of the phasor, this is the RMS value of this time domain function. So that's why we introduced the square root of 2 in the first place. We wanted, when dealing with phasors, to be dealing with effective values or RMS values. Take note that this is only one type of phasor transformation. Other books specify other types of phasor transformation. For example, our phasor transformation was based on the cosine function. Some books would base the phasor transformation on the sine function. Also, our phasor transformation deals with RMS values. Some books deal with amplitudes. If we were dealing with amplitudes, there would be no square root of 2. Let's have some transformation examples. So written here are the transformation rules, the top being the phasor transformation, the second line being the reverse phasor transformation. So first example, transform f1 of t 311 cosine 3770 plus 60 degrees to a phasor. What would be f1 of j omega, which alternatively we can write in this manner. The magnitude of the phasor should be the amplitude of the time domain function divided by the square root of 2. So that would be 311 over the square root of 2. And the angle of your phasor is just the phase angle of your time domain function. So this would be at an angle 60 degrees. Or this is just 220 at an angle 60 degrees. Let's say I had the phasor f of 2 of j omega, which is equal to 10 at an angle 20. What is its time domain equivalent? So here, omega is not specified. Remember, we said that omega is implied. So we have to express our answer in terms of omega. So what is f of 2 of t? The amplitude of my time domain function is the square root of 2 times the RMS value of my, or the square root of 2 times the magnitude of my phasor, because the magnitude of my phasor is RMS. No? So the amplitude of my time domain function would be the square root of 2 multiplied by 10. And then the argument of my cosine would be omega t plus the phase angle of the phasor. So this is just now 14.14 cosine omega t plus 20 degrees. In my third example, I'm given a sine function which I have to convert to a phasor. So this is a little bit tricky because our phasor transformation is based on the cosine function. So what I would have to do is convert the sine to a cosine. And that should be straightforward because we have the identity sine of theta is equal to cosine of theta minus 90 degrees. So this is really just the cosine of 377t minus 135 degrees. So what would be f of 3 of j omega? This would be 100 over the square root of 2 at an angle of minus 135 degrees, or simply 70.71 at an angle of minus 135 degrees. Let's take a look at what happens when we apply phasors to resistors. Consider a resistor whose voltage across it is V sub R and whose current through it is I sub R, where I sub R is a sinusoid with zero phase angle. From Ohm's law, we know that V sub R is equal to resistance times I sub R. So we get this expression for V sub R. Transforming V sub R and I sub R to phasors, this transforms to this. The phasor value of Rim cosine omega t would be Rim over the square root of 2 at an angle 0. And this transforms into this. Now, if we divide V sub R by I sub R, the ratio we're going to get is simply the resistance R. So this is the relationship that I wanted to derive. Let's park that for a while. Let's take a look now at inductors. So this is my inductor with my voltage across it, V sub L, and my current through it, I sub L. Where again, I sub L is a sinusoid with phase angle equal to 0. From V sub L equal to LdIL dt, we get V sub L is equal to minus omega L I sub m sine omega t. Because the derivative of cosine is equal to negative sine. What I want to do is I want to convert this to a cosine function because my phasor transformation is based on the cosine function. And I simply use the identity minus sine theta is equal to cosine of theta plus 90 degrees. If I transform V sub L and I sub L to phasors, so this is going to be transformed into this, and this is this. Again, if I divide V sub L by I sub L, what am I going to get? I'm going to get V sub L over I sub L. This is omega L at an angle 90 degrees. This is in polar form. Or if I shift to rectangular form, it is simply j omega L. Finally, let's take a look at the capacitor. So we have a capacitor with a voltage V sub C across it and a current I sub C through it. From V sub C equal to 1 over C, the integral of I sub C dt, we get this expression for the voltage across the capacitor. Again, we have to convert this to the cosine function because our transformation is based on the cosine function. So we use the identity sine of theta is equal to cosine of theta minus 90 degrees. Converting V's of C and I's of C to phasors, this now converts to this, and this converts to this. So getting the ratio of V's of C to I's of C we get 1 over C at an angle of negative 90 degrees. This is in polar form, or negative 90, that would be negative J. So 1 over C times negative J. But since minus J is equal to 1 over J, that is equal to 1 over J omega C. Let's define a new circuit parameter which we call impedance. Supposing this is a circuit element, we have the phasor voltage V sub j omega across it and the phasor current I sub j omega through it. The impedance of this circuit element is the ratio of phasor voltage to phasor current. Since this is a voltage to current ratio, the units for impedance would be ohms. I have already shown in the previous slides that for a resistor, the impedance of the resistor Z sub R is simply equal to its resistance. For an inductor, the impedance of an inductor Z sub L is equal to J omega L. And for a capacitor, the impedance Z sub C is equal to 1 over J omega C, or negative J over omega C. Reactance is the magnitude of the imaginary component of impedance. So if we just get the magnitude of the imaginary component of the impedance of an inductor, that would be omega L. And if we get the magnitude of the imaginary component of the impedance of a capacitor, that would be 1 over omega C. Note that if you want to convert reactance to impedance, for an inductor, you have to multiply that by J, but for a capacitor, you have to multiply it by minus J. Admittance is the reciprocal of impedance. Again, I have a circuit element with a phasor voltage across it and a phasor current through it. Admittance would be phasor current, ratio of phasor current to phasor voltage. Since this is a current to voltage ratio, the units for admittance would be Siemens, which is ohm to the minus 1. So from our previous expressions for impedance, we can get the admittances of a resistor, which is 1 over R, or equal to conductance. For an inductor, which is 1 over J omega L, which is equal to minus J over omega L. And for a capacitor, which is J omega C. Susceptance is the magnitude of the imaginary component of admittance. So for an inductor, this is just 1 over omega L, and for a capacitor, it is just omega C. By the way, the reactance of a resistor is 0 because a resistor has no imaginary component in its impedance. So only inductances and capacitances have reactance. Similarly, the susceptance of a resistor is also 0 because there is no imaginary component in the impedance of a resistor. Only inductors and capacitors have susceptance. We can now apply what we know about phasors and what we know about impedances to the analysis of circuits that are excited by AC sources. This is called the Phasor method of circuit analysis. It is also known as frequency domain analysis. What we actually analyze is a transformed network. How do you transform a network? First, you convert all AC quantities in that network into their corresponding phasors. Second, you replace all passive elements in that network into their corresponding impedances. In transform networks, the relationship between voltage and current for all circuit elements is algebraic. If you take out the relationship between voltage and current for the resistor or for the inductor or for the capacitor, nowhere there will you find any integration or differentiation. Therefore, Ohm's law, quote unquote, can be applied to all of these elements. Ohm's law now is stated as V is equal to Zi, where instead of resistance, it is impedance. So all networks now end up looking like resistive circuits because it's all just Ohm's law. And therefore, we can apply all methods of analysis developed for resistive networks. Let's take an example. I have here a series RL circuit that is excited by a sinusoidal voltage source of the form V sub m cosine of omega t plus alpha. What is the first step? First step is to transform the network. So how do I transform my source? My source, I transform into a phasor. So I have V's of j omega is equal to V sub m over the square root of 2 at an angle alpha. For my resistor, Z of R is simply equal to R ohms. And for my inductor, Z of L is equal to J omega L. So my transform network looks like this. I have V sub m over the square root of 2 at an angle alpha. And then I have R and J omega L. The resulting current from this circuit will be a phasor. We transformed the source into a phasor, so we expect the resulting current to also be a phasor. So this is going to be I's of J omega. What is the next step? The next step is to solve for the required circuit quantities using the transformed network. So this is our transformed network. We were supposed to determine I's of t. Thus, we have to solve for I's of j omega. Okay, this is equal to V's of j omega. This is equal V's of R of j omega, and this is equal to V's of L of j omega. From KVL, we know that V of j omega is equal to V of r of j omega plus V of L of j omega. V of j omega is V of m over the square root of 2 at an angle alpha. V of r of j omega is i's of j omega multiplied by r. And V of L of j omega is i's of j omega multiplied by j omega L. So this is simply equal to i's of j omega multiplied by r plus j omega L. Okay. Let me convert this now to polar form. So I get i's of j omega. Converting r plus j omega L to polar form, my magnitude would be the square root of r squared plus omega squared L squared. And my angle would be arctangent of omega L over r. So solving for i's of j omega, I get i's of j omega is equal to V of m over the square root of 2 at an angle alpha all over the square root of r squared plus omega squared L squared at an angle arctangent of omega L over r, which is simply V of m over the square root of 2 all over r squared plus omega squared L squared at an angle alpha minus arctangent omega L over r. This is in amperes. Don't forget the units, it's very important. What is now the third step? The third step is to transform the calculated quantities back to the time domain. Okay. So from step 2, I know that the magnitude of i's of j omega would be the RMS value of i's of t. So this is the RMS value of i's of t. And the angle of i's of j omega would be the phase angle of i's of t. So the RMS value of i's of t would be equal to V of m over the square root of 2 all over the square root of r squared plus omega squared L squared. And the angle of i's of t would be equal to alpha minus arctangent omega L over r. Sometimes, this is where our problem ends because this is the only thing that we are required to solve for. But if we want to convert i's of t back into time domain, which is what the problem specified, our time domain expression for i's of t would be equal to i's of t equal to, now what do we do with the RMS value? We have to convert this to an amplitude. So we have to multiply it by the square root of 2. So doing that, this now becomes V of m over square root of r squared plus omega squared L squared Okay, we're doing the reverse Phasor transformation. So we're in essence only taking into consideration the real portion of our phasor. And so that will be cosine of omega t plus this angle, alpha minus arctangent of omega L over R, amperes. So this is our final answer. If you had attempted to solve this not using the Phasor method, you would have had to solve a differential equation. So having done it in the Phasor method ended up being much simpler than having to do it in the time domain. Okay, let's do the exercise again. Let's now put actual numbers in the different parameters. So for example, Vis of t is 100 cosine 10t, our resistor is equal to 8 ohms, and our inductance is equal to 0.6 henries. This time we want to find Is of t and Vis of L of t. So what is step 1? Step 1 is to transform the circuit. First of all, we should recognize that our omega is equal to 10 radians per second. Okay. Now for the source, V, so let me use now the alternate notation, V is equal to 100 over the square root of 2 at an angle 0 degree volts. For my resistor, Zs of R is simply 8 ohms. And for my inductor, Zs of L is equal to J times omega L. Omega is equal to 10 and L is equal to 0.6. So this is J6 ohms. So what is my transformed network? My transformed network now is, I have V, which is equal to 100 over the square root of 2 at an angle 0 degrees. I have my resistor 8 ohms. And I have my inductance, which is J6. So this is equal to Vis of R, that's a phasor, and this is equal to Vis of L, which is also a phasor. And flowing in the circuit, we would have a current I, which is also a phasor. So this is my transformed network. So that's step 1. So step 2, I now need to solve for the required circuit quantities in the frequency domain. So I redrew here my transformed network. What do I have to solve for? I have to solve for I, and I also have to solve for Vis of L, because my unknowns are Is of t and Vis of L of t. So from KVL, I know that V is equal to Vis of R plus Vis of L. So this is 100 over the square root of 2 at an angle 0 degrees is equal to I. Vis of R is I multiplied by 8 plus I multiplied by J6, or simply I multiplied by 8 plus J6. I don't really have to convert this to polar this time. Why? Because solving for I get I is equal to 100 over the square root of 2 at an angle 0 degrees all over 8 plus J6. And I can solve this by just entering those numbers in my scientific calculator. That is because these complex quantities are completely specified. They are not specified, or no component is specified as a variable. So magically, I can just enter this in my calculator and I can get the value of I, which will now be equal to 5 times the square root of 2 at an angle of minus 36.87 degrees. This is amperes. Now what is V sub L? V sub L, my phasor, is equal to I times J6. Again, using my calculator, knowing this is my I, and multiplying that by J6, I'm just going to get 30 times the square root of 2 at an angle 53.13 degrees, and this is in volts. So the third step is to transform the calculated quantities back to the time domain, because it was required by the problem. So I, which is 5 times the square root of 2 at an angle of minus 36.87 degrees, in my reverse transformation will now be equal to, you multiply this by the square root of 2. So 5 times the square root of 2 times the square root of 2, I'm going to get 10 cosine omega is equal to 10, remember. So this is cosine 10t plus my phase angle, but my phase angle is negative 36.87 degrees. So this is going to be minus 36.87 degrees, and this is amperes. And V sub L, which is 30 times the square root of 2 at angle 53.13 degrees. Now I convert to V sub L of t. 30 times the square root of 2 times the square root of 2 is 30 times 2, which is equal to 60. Again, this is cosine of 10t. My phase angle is 53.13 degrees. And this is volts. Take note of the following. The difference in phase angle between I and V sub L is equal to 90 degrees. This is consistent with an inductor. In an inductor, the difference in angle between the voltage across the inductor and the current flowing through the inductor will be 90 degrees. 90 degrees, no? Negative 36.87 minus 53.13, that's minus 90 degrees. The difference is 90 degrees. Second, we see that V leads I, or I lags V. So again, that's consistent with an inductor. Before we leave this exercise, I'd like to point out that the Phasor method can only be used to determine steady state response. In other words, this is steady state response. We cannot use the Phasor method to determine transient response. You're going to learn other methods in your future EEE courses that will allow you to determine what are the transients that will exist in the circuit the first time you put the circuit together. So the steady state response is the response after the transients have disappeared. So I said for frequency domain analysis, we can use all methods of analysis developed for resistive circuits. That means we should be able to do network simplification. What is network simplification? We should be able to simplify impedances in series and impedances in parallel. You can also do Y to delta and delta to Y conversion. By the way, we did not take up Y to delta and delta to Y conversion in resistive networks, so you don't really have to worry about this too much. We can use the principle of voltage divider and the principle of current divider. We can do node analysis. We can also do mesh analysis, but mesh analysis you also haven't taken up yet. We can apply the principle of superposition, and we can apply Thevenin's and Norton's theorem. The second part of this module, I'm going to give examples of the application of each of this. In the meantime, go through this module very carefully. Try to master the contents of this module so that you'll be able to keep up when you view the part 2, when you view part 2 of module 12. Thank you.